Hey everyone, and welcome back for another deep dive. Today we're going to be looking at grokking.
Grokking.
Yeah, it's this really interesting phenomenon in depth learning, and
Yeah.
I think it's one of those things that like once you see it, you're like, whoa, okay, there's something really profound going on here.
Right.
So we're going to be looking at a couple of academic papers all about grokking, and they're really trying to get to the bottom of why it happens.
Yeah.
But we're also going to be talking about like why this even matters,
Yeah.
Like why should anyone care about grokking even if they're not, a deep learning expert,
Yeah. And, it kind of throws a wrench into a lot of the assumptions we make about machine learning.
right?
We usually expect these models to kind of gradually improve.
Yeah.
But with grokking, it's like, bam, they suddenly get it.
Exactly. And what's even weirder is that some of the research we're looking at today is saying that this whole grokking thing might actually be tied to like,
Oh,
yeah, to like these tiny little errors that happen when computers try to represent numbers, like those floating point errors.
interesting.
So those tiny little rounding errors that we usually just ignore,
Right.
they could actually be like a major roadblock to grokking.
Yeah. And in fact, the researchers are actually looking into this because they're trying to figure out why, in some situations where they expected models to grok, the models just kind of ended up overfitting to the training data.
Oh, so they were expecting to see grokking, but they just got stuck in that overfitting rut.
Yeah, exactly. And what they found was that these tiny errors that we normally think of as insignificant can actually be a big problem.
Wow, so like those tiny little rounding errors can actually stop a model from making that big leap in understanding. That's pretty wild.
It is. And specifically what they found was this phenomenon that they call Softmax Collapse.
Softmax Collapse.
Yeah. And basically what's happening is the model's calculations are getting so extreme that the computer can't really represent them accurately anymore.
Okay, so help me break this down a bit. I know softmax is used in neural networks to like calculate probabilities, right?
Right.
So how does this collapse thing actually happen? And like why does it prevent grokking?
So think about it this way.
Yeah.
As the model is training, it's getting more and more confident in its predictions.
Okay, yeah.
So it's like its internal confidence scores or logits are getting really, really big for the correct answers
Mm-hmm.
and really, really small for the incorrect ones.
Okay, so it's like a seesaw where one side is way up in the air and the other side is practically scraping the ground.
Exactly. And that's where the problem comes in, because when those logits get too extreme, the computer essentially rounds off the tiny probabilities for those incorrect answers to zero.
Oh, so it's like the model is saying, nope, those other answers don't even exist.
Right. And that means it stops learning effectively because it's not getting any feedback on its mistakes anymore.
So it's like even though there might be a better solution out there, the model is stuck in this loop of thinking it's always right.
Yeah, exactly.
Yeah.
It's so focused on what it thinks it knows that it becomes blind to other possibilities.
And that's why we don't see that aha moment of grokking.
Right.
Okay, so we've identified the problem, but what do we actually do about it? Did the researchers find any ways to like prevent this softmax collapse from happening?
They did. They actually came up with a pretty clever solution.
Okay, I'm listening.
They basically said, well, if softmax is causing the problem, let's just replace it with something that's more robust.
Okay, I like it.
So they developed this new activation function called StableMax.
Stable max.
Yeah, that's specifically designed to handle those really extreme logits without falling apart.
So StableMax can help these models actually achieve grokking even without those regularization techniques we usually use.
That's exactly what they found.
That's really interesting. But now I'm kind of wondering, like, why did these errors happen in the first place? Is it just like a quirk of how computers work with numbers, or is there something deeper going on?
That's a great question. And it actually leads us to another key concept that the researchers were exploring.
Ooh, laid it on me.
It's called naive loss minimization.
Okay. Naive loss minimization, or I guess NLM for short.
Right.
What is that all about?
So imagine you're trying to learn a new language,
Okay.
but instead of actually like understanding the grammar and vocabulary,
Yeah.
you just memorize a bunch of phrases to pair it back.
So it's like cramming for an exam without actually learning the material.
Exactly. You might be able to get some things right, but you don't really get it.
Right.
And that's essentially what NLM is.
So the model is finding a way to reduce its error during training.
Right.
But it's not actually like deeply understanding the problem.
Exactly.
Okay, so how does this NLM thing lead to those like super extreme logits and that softmax collapse we talked about?
So with NLM, the model is basically focused on getting the right answers,
Mm-hmm.
but it's doing so by just inflating its confidence scores for those answers.
Okay, so it's like instead of refining its understanding, it's just like shouting its answers louder and louder.
Exactly. And as you can imagine, that shouting eventually leads to a breakdown of the system.
Ah, and that's where those numerical errors come in.
Right.
It all starts to make sense now.
And the researchers found that this NLM behavior is particularly common in certain types of neural networks.
Oh, really? Which
They're
ones?
called homogeneous networks.
Homogeneous networks. Okay, I'm not familiar with that term. What are they?
Basically, they have this specific mathematical property where if you scale their weights, their output also scales proportionally.
Okay.
And this makes them really susceptible to NLM because they can easily reduce their error just by scaling up their weights,
Yeah.
which in turn scales up their logits.
Ah, so it's like a recipe for disaster. You have this overconfident model that's focused on superficial learning,
Right?
and it's sitting in this network that makes it super easy to just keep inflating those confidence scores. No wonder things go haywire. But did the researchers just like identify the problem, or did they actually come up with a solution for this whole NLM thing?
They did. They came up with this really cool
Oh,
solution.
tell me more.
It's a new type of optimizer that they call GRUD.
Grod, okay. And how does that work? Does it like prevent that NLM problem from happening?
It does. What it does is it makes sure that the model's updates are only based on the parts of the gradient that are orthogonal to the direction of the weights.
Okay, I think you lost me a little bit there. Orthogonal. Is that like a geometry term?
It is, yeah. So think of the direction of the weights as a line.
Okay.
What GROD does is it makes sure that the model only updates its weights in directions that are perpendicular to that line.
Oh, so it's like RGRAD is forcing the model to explore different paths to the solution
Right.
instead of just running in the same direction and getting stuck.
Exactly. And this approach has actually shown some really promising results.
Like what?
Well, models that are trained with RGRAD tend to generalize much faster.
Oh, that's great.
And they often avoid that initial overfitting phase that's so characteristic of grokking.
So it's like they're skipping that awkward cramming stage and going straight to true understanding.
You could say that. And what's even more interesting is that this new understanding of NLM and Softmax Collapse helps explain why some existing methods for inducing grokking actually work.
Really? Which methods are we talking about here?
We'll take weight decay, for example.
Okay, yeah, that's a pretty common technique to prevent overfitting.
Right. But now we can actually see it through this lens of NLM.
Oh, so how does that work?
Well, weight decay can actually be seen as a way to mitigate the effects of NLM.
So it's like a gentle nudge that keeps the model from getting too confident and running into those numerical errors.
Exactly. It's a way of keeping the model grounded, so to speak, preventing it from getting lost in its own echo chamber.
Wow, this is incredible. It's like we're starting to see how all these different concepts in deep learning are actually interconnected. But before we get too carried away here, let's bring it back to our listener for a second. Why should anyone care about all this technical stuff about grokking and numerical stability?
That's a really important point. Not everyone's a deep learning researcher.
Right.
But the thing is, the implications of this research go way beyond just understanding this one weird phenomenon.
There, so.
Understanding these underlying mechanisms of how models learn can help us design and train better deep learning models.
Okay. Yeah.
And that's across all sorts of different fields.
So whether it's like computer vision or natural language processing or even robotics, these insights could help us create AI systems that are more efficient and reliable.
Exactly.
So it's not just about grokking itself, it's about understanding the fundamentals of how machines learn so we can build better AI in general.
That's the big picture here.
Okay, I like it. And this research specifically focused on algorithmic tasks.
Mm.
But do you think these principles could apply to other more complex tasks, like those involving vision or language?
Absolutely. It's definitely possible. I mean, imagine if we could induce grokking-like leaps in understanding in areas like scientific research,
Whoa, yeah.
or even creative problem solving. That would be amazing.
That's a really intriguing thought. If we could harness that power of sudden insight, who knows what breakthroughs we could achieve.
It's an exciting prospect for sure, but we need to be realistic here. We are still in the early stages of understanding grokking.
Right.
There's a lot more research that needs to be done before we can even begin to think about those kinds of applications.
Yeah, we need to approach these ideas with a good dose of scientific rigor. But it's still fun to think about the possibilities.
Absolutely.
Okay, so we've covered a lot of ground already in this first part of our grokking adventure. We've learned about this mystery of delayed generalization
Right.
and the role of floating point errors and softmax collapse, and this whole intriguing concept of naive loss minimization.
It's a lot to take in.
It is, but we're not done yet. We'll be back in the next part to delve even further into the implications of this research, connect the dots with some existing Grokking-inducing methods, and leave you with some thought-provoking questions to ponder. So stay tuned and keep those brains engaged.
See you soon.
Welcome back to our deep dive on Grokking. Last time we were talking about how those tiny numerical errors can actually have a huge impact on whether a model can make that leap to true understanding.
Yeah, and we were talking about those cool solutions like StableMax and YourGrad to kind of tackle those floating point errors and that whole naive loss minimization thing.
Right.
And you mentioned that this new understanding of Grokking also kind of sheds light on why some existing methods for actually inducing Grokking work.
Exactly.
But I'm really curious to hear more about that. Like, what kind of methods are we talking about here?
Well, let's start with weight decay.
Okay, so weight decay, I know that's a technique we use all the time to prevent overfitting.
Right, but now we can kind of see it through the lens of this NLM thing.
Okay, yeah, remind me how that works again. So NLM, it pushes the model to just inflate those confidence scores.
Right, which can lead to that Softmax collapse.
Exactly. And weight decay, it actually acts as a counter to that. It's like gently pulling back on the reins to prevent the model from getting too overconfident and running into those numerical instabilities.
So it's not just about preventing overfitting in the traditional sense.
Right.
It's also about maintaining some kind of balance in the model's calculations.
Yeah, to kind of avoid those catastrophic collapses.
Okay, that makes sense. Another thing that I found really interesting in the research was the use of MSE loss.
MSE loss.
Yes, so mean squared error loss on these shallow networks.
Right.
And they found that in some cases you can actually get grokking without any regularization when you use MSE loss.
Yeah, it's kind of surprising since we've been talking so much about cross-entropy loss.
Right, exactly. So why does MSE loss behave so differently? Is it something about the way it handles those increasingly large logits we talked about?
Yeah, you're on the right track. With cross-entropy loss, the model can basically keep reducing its error just by scaling up those logits.
Right.
Even if it doesn't really understand the problem at all.
Which is like the whole essence of NLM.
Exactly. But with MSE loss, there's a limit to how much the model can actually benefit from that kind of inflation.
Right.
At a certain point, those inflated logits actually start to increase the error.
So it's like MSE loss has this built-in safeguard against NLM.
Yeah, you could say that.
It's like a natural form of regularization.
Right. But it's worth noting that this effect seems to be less prominent in deeper networks.
Oh, really?
Yeah, maybe the complexities of those deeper architectures
Yeah.
allow NLM to kind of sneak back in, even with MSE loss.
So there's still a lot we don't know about how different loss functions interact with this whole grokking thing.
Definitely an area for more research.
For sure. The research also mentioned this thing about scaling weights.
Scaling weights.
Yeah, as a way to delay generalization. And I thought it was interesting that this technique can actually make Softmax collapse more likely.
It's all about finding the right balance right.
Right.
So we were just talking about how weight decay it helps prevent those collapses.
Yeah, by pulling back on the weights.
Exactly.
Right.
But scaling weights does the opposite. It pushes them forward. So it's kind of like a tug of war.
Okay, I see where you're going with this.
If that scaling force is too strong, it can actually overwhelm the stabilizing effect of weight decay.
And then, bam, those laws just go through the roof.
Right, and softmax collapse becomes much more likely.
So even these techniques that seem really straightforward
Yeah.
can have these unintended consequences if we don't really understand what they're doing to the model's training process.
Exactly. This research is really giving us a valuable look under the hood of these deep learning models.
It is. How do you think these findings about scaling weights relate to grokking itself?
Well, what the researchers found is that while scaling weights can delay generalization,
Right.
it doesn't necessarily lead to grokking.
Okay.
Even with really extreme weight scaling,
Mhm.
they found that grokking often didn't occur.
So it seems like just delaying generalization isn't quite the same as inducing that aha moment.
It might be that delaying generalization just prolongs that overfitting phase
Yeah.
without leading to that crucial shift in understanding.
So it's like the model is just spinning its wheels.
Right. It's not really getting anywhere.
This makes me think back to something we talked about earlier.
What's that?
That idea that maybe grokking isn't limited to just these algorithmic tasks.
Right.
Like, remember the researchers kind of hinted at the possibility of inducing grokking like leaps in understanding in other fields?
Yeah, like scientific research or even creative problem solving.
Exactly. So if we could unlock the secrets of this sudden emergence of understanding,
Yeah.
could we potentially use that knowledge to enhance human cognition?
That's a really interesting thought. But it's important to stay grounded here. We're still in the very early stages of understanding grokking. There's so much more research to be done before we can even start to speculate about those kinds of applications.
Oh, for sure. We need to approach these ideas carefully. But it's still exciting to think about the possibilities.
Absolutely.
The more we learn about how machines learn,
Right.
the more we might actually discover about our own learning processes.
That's a great point.
So what do you think are the key takeaways from this research on grokking?
I think one of the biggest takeaways is that grokking, it's more than just a curious quirk of deep learning.
Okay.
It's really a window into the fundamental processes of how these machines actually learn.
And by understanding what leads to grokking and what prevents it,
Right.
we gain these valuable insights into the inner workings of these deep learning models.
Exactly.
It feels like we're moving away from this trial and error approach to machine learning and towards one that's guided by a much deeper understanding of the actual underlying principles.
I think that's a really good thing.
Yeah, it has to be right.
This shift in perspective, I think it can lead to AI systems that are more robust, reliable, and interpretable.
So, for example, knowing about the risks of Softmax Collapse might lead us to explore different activation functions.
Right, or training regimes that are more numerically stable.
And understanding NLM could inspire us to come up with new optimization techniques.
Yeah, that actually encourage models to seek out true understanding.
Instead of just relying on those superficial pattern matching tricks.
It's all about guiding those models toward true generalization.
Right. But like any scientific endeavor, there are still a lot of unanswered questions.
Absolutely.
For example, we've been focusing mostly on homogeneous networks
Right.
when we talk about this NLM stuff. But more research is needed to understand how these dynamics actually play out in these more complex architectures that aren't strictly homogeneous.
Yeah, because real-world deep learning models are often incredibly complex.
Yeah, layers upon layers of interconnected components.
Extending these findings to more realistic settings, I think that's going to be crucial for really realizing the full potential of this research.
Absolutely. Another open question that I keep thinking about is like the suddenness of grokking.
Yeah. So we talk about how these models suddenly get it after this period of overfitting, but what is it that actually triggers that transition?
Right.
Is it a gradual process that's just like masked by limitations in how we measure performance?
Yeah.
Or is there like a genuine shift in the model's internal state?
That's the big question, isn't it?
It's like we're witnessing some form of cognitive metamorphosis in these models.
Yeah.
And we're still trying to figure out what's driving that transformation.
It's a really exciting area of research.
It is. So it sounds as we've covered a lot of ground in this part of our deep dive.
We have.
We've seen how this new understanding of NLM and Softmax Collapse helps explain why these existing Grokking-inducing methods like weight decay and MSE loss actually work.
Right.
We've talked about the nuances of scaling weights and how it can kind of influence the grokking process. And we've even touched upon that really tantalizing, though still speculative possibility of using the power of grokking to enhance human cognition.
Some really big ideas to think about. They are. But this is just the beginning of the journey.
It is.
There's so much more to discover, more questions to ask, and more mysteries to unravel.
Definitely.
We'll be back for the final part of this episode to wrap things up and leave you with some thought-provoking questions to ponder.
Sounds good.
See you soon.
See you soon.
And we're back for the final part of our deep dive into grokking. It's been quite a journey exploring this strange phenomenon in deep learning where models just suddenly seem to get it?
Yeah, it really is fascinating, isn't it?
It is, and we've uncovered some really surprising connections along the way.
We've seen how even like those tiny numerical errors can have a huge impact on a model's ability to grok.
Right, and those things like softmax collapse and naive loss minimization
Right.
can really throw a wrench into the learning process.
Yeah, they can really derail things.
But we've also learned about some pretty clever solutions like StableMax and eGrad to help overcome those challenges.
Right? And what's really cool is that this research is also helping us understand why some of those existing techniques like weight decay and using MSE loss actually work in the first place.
Yeah, it's like we're getting this bigger picture of how all these different concepts in deep learning are connected.
It's all starting to click into place.
So as we wrap up this deep dive, what would you say are the most important takeaways from this research on grokking?
I think the biggest takeaway for me is that grokking, it's more than just this weird quirk of deep learning, you know?
Yeah.
It's really a window into the fundamental processes of how machines learn.
And by understanding the conditions that either lead to grokking or prevent it,
Right.
we get these valuable insights into how to actually design and train better deep learning models.
Exactly.
So it's like we're shifting away from this trial and error approach
Yeah.
and moving towards a more like principled understanding of machine learning.
I think that's a really good thing.
It has to be right. It should lead to AI systems that are just better all around.
Absolutely.
Yeah.
More robust, more reliable, and easier to understand.
So, for example, knowing about Softmax Collapse, that might encourage us to explore other activation functions that are more numerically stable.
Right. Or come up with different training methods.
And if we understand naive loss minimization,
Yeah.
that might lead us to new optimization techniques that encourage models to really understand the problem they're trying to solve.
Instead of just finding those shortcuts.
Yeah, just to minimize the error during
Correct.
training.
It's all about guiding those models towards true generalization.
But like any scientific field, there are always more questions to ask.
Oh, definitely.
For example, we've mainly been talking about homogeneous networks and NLM. What happens in these more complex architectures that aren't homogeneous?
Yeah, that's a great question.
Because real-world models are incredibly complex.
Layers upon layers.
Figuring out how grokking works in those settings is going to be really important.
Absolutely.
Another question that I keep coming back to is the suddenness of grokking. What triggers that aha moment?
Right. Is it gradual, or is there some kind of internal shift in the model?
It's almost like we're seeing this cognitive leap in these models.
It's a really intriguing idea.
And we're still trying to figure out the mechanisms behind it.
It's all part of the mystery.
It feels like we've only scratched the surface of this topic. There's so much more to learn about grokking and what it means for the future of AI.
If you're interested in diving deeper, I definitely recommend checking out the research papers we've been discussing.
We'll include links in the show notes. And as always, we love hearing your thoughts.
Yeah. What are your biggest takeaways from this deep dive? What questions are you still thinking about?
Share them with us on social media and keep this conversation going.
And that brings us to the end of our deep dive into grokking.
We've covered a lot of ground, explored some really fascinating concepts, and hopefully sparked some new ideas.
It's been a great discussion.
It has. Thanks for joining us on this journey of discovery. And remember, the pursuit of knowledge is always best when it's shared.
So tell a friend about what you learned and keep that curiosity burning bright.
Until next time, keep exploring, keep questioning, and keep learning. We'll see you on our next deep dive.